This is a preliminary design vacuum distillation column of ethylbenzene and styrene done by Yu Jiaxuan. Vacuum distillation is defined as a distillation technique that operates under reduced pressure, allowing the evaporation of liquid component at significantly lower boiling points than the standard atmospheric pressure. Styrene is thermosensitive, where it is prone to polymerize without any inhibitors added, starting from 100 to 300 degrees Celsius. The unique operation is the tray-based vacuum distillation column, where the binary mixture is ethylbenzene and styrene. The feed condition for this separation process is at 100 kmol per hour and at saturated liquid, and the target purity of the separation is 99.7% of ethylbenzene at distillate and 99.8% at the bottom for styrene, where it meets the condition of the industrial styrene monomer. The core objective of this project is to determine a preliminary design which accounts for flooding and height constraint while considering the indirect carbon dioxide from duty of condenser and reboiler. The separability of binary mixture of ethylbenzene and styrene has been done through relative volatility estimation using the thermodynamic equation such as the Anton equation, where the relative volatility ranges from 1.36 to 1.32 calculated using the partial pressure of ethylbenzene and styrene. This proved that the mixture is separable. The approach of shortcut method in HYSYS has been done where the logic behind the shortcut column was the FUG method, which is Stefanski-Underwood-Gillen. It is used to determine the minimum reflux, the minimum number of tray, the actual number of tray, and the optimum feed stage within a distillation column, where the actual number of tray will be used for later calculation on column height as well as the simulation on the rigorous distillation column within Aspen HYSYS. These are the results tabulated for column diameter sizing accounted for flooding using FAS, Lowenstein, and Aspen HYSYS. And FAS will act as the differences basis as shown in the slide's equation. It can be seen that Aspen HYSYS calculation of diameter is very near to FAS, due to the selection of tray is sieve tray, and FAS specifically focuses on sieve tray or valve tray diameter. This is a trial and error example approach of internal diameter in Aspen HYSYS rigorous distillation column. As we can see, the automated diameter is around 4.25 and is later scaled up to 4.4 meter, and the results of loading after tuning it is around 75%. And we can see that the operating point further away is from the max entrainment limit, which means it is further away from flooding. The actual number of trays are calculated after dividing the actual theoretical tray from shortcut HYSYS using the efficiencies of 0.7. As we can see, from 1.5 reflux ratio to 2.5 reflux ratio, the number of trays decreases and the column height decreases below 53 meter, which avoids the wind load limitation from the rule of thumb. The first table shows the duty estimation through both Aspen HYSYS and MATLAB Ponchon coding. The second table shows the indirect carbon dioxide emission in kilogram per hour calculated from the duty in kilowatt per hour, where the trend of carbon dioxide increment can be seen from 3,900 to 6,300, ranging from the reflux ratio multiplier of 1.5 to 2.5. In conclusion, a preliminary design of vacuum distillation column for the separation of an ethylbenzene and styrene binary mixture has been successfully developed by balancing the two constraints of structural towel height and hydraulic entrainment flooding while integrating indirect carbon dioxide emission as an essential sustainability consideration. The 5 distinct reflux ratio chosen are 1.5 times of minimum reflux ratio, 1.8 times, 2 times, 2.3 times, and 2.5 times, and they have all been evaluated throughout the presentation. The reason why reflux ratio before the multiplier of 2 has not been considered is due to it violates both rule of thumb of 53 meters column height, and there is only limited existing crane which could reach height over 50 meters and 60 meters, thus causing issue when installing the humongous column. Meanwhile, 2.3 times of minimum reflux ratio has came out as a sweet spot in between the range of chosen reflux ratio. as it has a diameter of 4.2 meters compared to 2.5 times of minimum reflux ratio at 4.4 meters diameter. Also having a safe column height around 47 meters, which didn't differ a lot from 2.5 times of minimum reflux ratio. Moreover, it has a duty of below 8,000 kilowatt, and the indirect carbon dioxide emission is lesser than 6,000 compared to 2.5 times of minimum reflux ratio. Thus, it became the best. If you have any question, please leave a like and comment below. Thank you.